Chris Hilt, and 27 years ago, I founded CLH Design. We're located in Cary. We are a civil engineering and landscape architecture firm, and what we specialize in is school design. So a lot of you, the schools that you're at, we've probably touched them in one way or another over the past 27 years because we've done almost 200 projects for Wake County schools. Wake Tech as well is a client of ours, so we do a lot of work with them. Our emphasis is environmental stewardship. There are 22 of us, and many of our projects, including the one that we're going to talk to you about today, has a very strong environmental education component. The other thing that we're very proud of is 55% of the professionals in our firm are women. We're working very hard to increase the diversity also with African Americans, and I'm going to be very happy to introduce to you soon two of our bright stars and emerging professionals who are going to carry you through these math equations.
Good morning, everybody. I'm Steve Miller. I'm the picture way on the right. I've been a partner with Chris for a little bit over 20 years now. I'm a civil engineer.
Hi, I'm Danny. The second photo from the left. I'm a civil designer here at CLH. I've been working here for 3 years now.
My name is Joshua Alanugia. I'm a landscape designer, trained to be a landscape architect here at CLH Design. Been here about 4 years. I guess I could start talking about what led me to this career. I was in the advisor's office. I went to Wake Tech actually. I was actually studying for architecture, and I wasn't quite satisfied. Nothing against architecture, but I just wasn't quite satisfied. And he said, "Well, are you landscape architecture?" And from then on, I said no, and he kind of described it to me in a nutshell, and that's how I made the switch. It was that simple. From what he told me, it was all about outside of the building, and I thought that was a cool aspect, and that's kind of what led me to my career here at CLH, which started with the internship towards the end of my associate's degree at Wake Tech. That's right. And what I like most about the career is where I always describe to people with a building, you kind of pass by it on the road. You may not get to appreciate what actually happens inside the building. And with site design, it stands the test of time to an extent. It also shows the progress of time. You can go from nothing to something, over a few months, and you drive by a site and you can really appreciate that every time you drive by that site. From the landscape to the storm water management in a nutshell. And some of the challenges of the career, I would say, it's very high demand. High demand, but there's good in that. You're constantly wanting to reach that next level. You get new challenges every day on site, new problems you have to work out, and these are real world problems, and it's kind of put in our hands to kind of guide the client through that.
Like Joshua, I started, architecture is very popular, like in culture in general, because you walk by a building and you ask, like, who built that type of thing? And you see it in movies and TV shows, but I guess landscape architecture and civil engineering don't get as much hype. So when I was in high school, I wanted to go into architecture, but I also really liked like environmental sciences and math, and my mom kind of nudged me into civil engineering. And when I was in school, I really enjoyed city planning and transportation and hydraulics. So like that kind of made me go more into site design instead of structural engineering or something more building based. And for my internship, what I did was I studied in Argentina, and I worked for the Ministry of Water down there doing my thesis, and we developed maps for the design storms for different regions. So that kind of like pulled me into more of the stormwater design part, and I really enjoyed that. like Joshua said, this is a very demanding job sometimes. We have hectic schedules, just because a problem may pop up in a job site, or uh, a client wants to change something last minute, anything like that. But it's very rewarding to actually be able to impact the places we live in, like just from improving the commute for somebody, adding a road, or uh, designing a school where children will play and spend their time, or doing a park, anything that kind of improves the environment that you're in, and also takes into conscience the environmental impact that we're leaving behind. So it's a very rewarding job. And some of the qualities that we think are very important for somebody working in this field would be having good communication skills, be it verbal or written. Because sometimes whenever you think of engineers, you think you're in this bubble, you're all numbers, you don't have to interact with people. But you do. You need to interact with your coworkers, you need to interact with your managers, you need to interact with reviewers, reviewing your plans, with clients, with contractors. It's very important to be able to communicate well, and also to be organized with how you do your work. I remember in high school, I used to get so frustrated when I got points taken off or skipping steps, because they were very obvious steps in my head. But it's so important to be very thorough and to leave things everywhere you work, because you don't know 3 years from now if somebody asks you something about a project. You need to be able to go back and look at it and know what you did, or your coworkers, if you're out on vacation, need to be able to pop into a project and fix something if a contractor calls because there's an issue. So it's very important to be well organized and communicate properly.
We work with two different types of professionals in our office, being landscape architecture and civil engineering. And Danny and I actually collaborate many times throughout our careers here at CLH, because we break our office into teams and we work on different projects and teams. And the two different professions kind of merge together to put out these great projects. So communication is essential for this job. And with communication comes writing, because you have to talk to clients and reviewers and people and planners who are going to approve your plans. So email, something as simple as an email, holds a lot of value in being able to write clearly and legibly and understandably, and really whatever sender is, whoever the recipient of these emails are, they need to know exactly what you're talking about, especially when you're working with deadlines. So emails, communication, writing are all also very important skills in our profession.
Talking about the salary range, starting landscape architect usually around 45,000, starting engineer 55. Can be a little bit higher depending on whether it's an undergraduate degree or a master's degree. And a lot of that also depends on the state of the economy. So there's some fluctuation there. But once both receive licensure, which takes usually 3 to 4 years of internship and apprenticing, then that can jump up significantly. And the paths to licensure are very diverse. Engineering, you can actually not have an engineering degree, and in 15 years of working under an engineer, you can become licensed. We have an engineer like that. He's a partner in the firm. And then we have folks like Joshua who will take a 10-year path through the landscape architecture apprenticing, and because he does not have a degree. So there are a lot of different options in an effort to increase the diversity in the profession.
So here we have, this is before the pandemic, this is what we would look at every day when we came into work. As you will see, we're not necessarily in walled cubicles. It's an open design, kind of enforces the collaboration. And I say enforce because we really believe in collaborating as a firm as one of the keys to how we're able to put these projects out. And on to the right, kind of showing you this is a drafting table where we still do hand sketches. Chris and some of the other people in our office do amazing hand sketches and renderings for these sites, because it's kind of preliminary for the client to transfer ideas quickly and effectively and in a beautiful manner. And so that there is a mix of both computer and hand skills in our profession. And, here is the what we call the war room, the print room. This is where the stuff happens, where we've done all our work and we're getting things packaged up and we're getting ready to send out. And we're either sending it to contractors, plan reviewers, clients, the owner of whatever property we're working on. And so this is where we've done our hard work and we're putting it out and we're sending it out to the world. There's a table in the back corner where we have our team meetings, and that's just another nod to collaboration. We do a lot of that. Each team has a meeting typically every week. We go over the week, what deadlines are due, and it's just another look into our everyday world.
Usually we'll do most of our calculations in spreadsheets. A lot of the times it's not very, I mean, it's complicated calculations, but everything can be done in spreadsheets. We also use other programs for the routings, and we mostly design in AutoCAD. We'll design it on the computer and then create our sheets, which we submit to the owners or to the reviewers of what the actual plans look like.
With AutoCAD, this is the end product of AutoCAD. AutoCAD is where we do all on, and AutoCAD stands for computer aided drafting. That's the CAD part. And this is kind of where we do a good chunk of our work to produce these drawings. I know I personally use it a lot. And this is our end product. And what you're looking at here is a grading plan, which we will go in depth at as part of some of our exercises. This is actually a grading plan from the project that we'll be taking these problems from. And then the next slide is a landscape plan, which is kind of, that environmental part that we're talking about. Part of the reason we have landscape plans is to make sure that we're not just paving the world and not really repopulating some of what we've taken down as far as vegetation goes. And again, this is another AutoCAD product, and this is what the end result of the plans will ultimately look like. And then here is the kind of pre-COVID and post-COVID. The left will be pre, and the right will be pro, or not pro, I'm sorry, post-COVID. And this pandemic is a reality, and there's a silver lining in it. It's teaching us different ways to communicate effectively. So on the left, where this was a typical thing we would do in the office, we'd sit over plans and review things and red line plans, which were just revisions. We're clouding and marking and making notes so we can go back to the drawings and revise. And on the right, this was actually a presentation of ideas done via Microsoft Teams, which is another format similar to Zoom, which some of you may be familiar with. Typically, we use Microsoft Teams in our office. It's just easier to use for how we can have things set up. And on the left here, you see materials. So these are some site materials. A lot of times before we put things on plans, we'll want to get samples. And because, a picture is one thing, but to actually feel it and see it and hold it, you kind of see what you're dealing with, as well as getting a scale of what you're putting out there on these projects. This is our handy dandy Maglin table, which was actually a gift from one of our suppliers of our site furnishings, because we use them so much, and it's just making relationships, which is also important in our field. And here's our work truck. we may or may not need to work on our parking skills. But and on the to the right, you'll see that's actually Danny and myself out at a project we're doing what's called a punch list, which we kind of go out to the site and we're making notes on the drawings. If things don't add up with what our drawings say, we're making notes and having the contractor correct those things. Here's our site. This is our focus of the problems we'll be doing. South Lakes Elementary School, the San Fuquay Arena. As you see the school building down there to the south, we have 2 parking lots. We have a smaller field in the middle that's mainly for the elementary kids. And we also have 2 fields towards the north, which are for future community center. So we had to kind of grade out the site and plan accordingly, kind of planning for the future. And the wetland, focus wetland, I should say, is the one at the very bottom of the screen. That guy right there. One of those wetlands didn't make it through the full project, which is that one that's off to the east of the project, right near the drive. But that's just the evolution of design. You find that you don't need necessarily all the wetlands that you're going through the design process.
There are federal, state, and local municipality regulations for stormwater. And there's basically 2 things that we analyze. We look to control the stormwater quantity leaving the site and the stormwater quality leaving the site. So on stormwater quantity, what we want to do is maintain the same amount of water that was leaving the site before we went in and constructed something. Needs to be maintained. We cannot allow more water to leave the site because that would cause problems downstream of the project. There's multiple ways we can detain the quantity. We can have ponds, be it dry ponds, wet ponds, or we can even have cisterns that they can be above ground or below ground. So from the quality standpoint, we have to analyze how the state of the water when it leaves the site. So if you imagine you have woods, they're pristine woods, there's nothing in there that is going to pollute the water. But once we build the site, imagine a school, you're going to have fields, for example, and you don't think about fields being pollutants, but you have to think that to have those beautiful green fields, you're going to need pesticides, you're going to need fertilizers, herbicides, you're going to need a lot of things. And also you're going to have like parking lots where cars park, they're going to leak oil. There's a lot of things. And once it rains there, all that it gets washed down. So we need to detain the water and hold it enough time so the particles drop down. And also we can have plants in there that will consume the nitrogen and phosphorus from the fertilizers and avoid that going into our stream system. And it's very important also to analyze the conveyance of the stormwater. So we need to study how the water moves through our site and once it leaves the site. So for this, we'll design stormwater pipes that we have there. We can see in the first image, that's just a pipe that goes underneath the ground. And we can also have channels. But what's very important when we do this is to size them so they have the capacity to carry the water so it won't flood upstream or downstream of us. And also, we play with the velocity so that will not cause erosion downstream of us.
So what we have here is the far left. This is our site before the initial clearing. It was actually an old peanut field. So basically what we would categorize, this is a virgin field, has never had anything built on it other than a peanut field. Jump to the right picture, actually. So that is a little earlier on in the process. The site's not complete, but it's getting there. Down there is our wetland subject, which is now acting as a sediment basin in that far right picture. So basically during construction, that's where all the sediment drainage is going. And in the middle is when it's starting to form into a wetland. They're starting to move dirt around and kind of finalize how that's going to look.
So for the first thing we do when we do the analysis for the site, we'll determine the amount of water leaving the site. And we call this the peak discharge for the pre-development condition. To do this, the first thing we're gonna analyze is we're gonna try to determine the runoff coefficient. And the runoff coefficient basically depends on the type of soil we have and the type of ground cover we have. So there are many types of soils, and all of them work differently. They are subdivided into 4 types of soil. And in this site, for example, we had type A and type B. So we can have sandy soils that if we think about it, you can always see sand allowing more water to drain through it. And then you can have, for example, more clayey soils, which, you know, they don't absorb much water. The water will absorb a little and then it just starts sheet flowing. So that's why the soils are important in our analysis. And the type of ground cover that we have will affect if the water can infiltrate or if it just sheet flows off. So for example, if you have a grass lawn field, or if you have a forest, it'll be different, or if you have impervious surfaces. And we consider impervious surfaces any type of surface that won't allow water to drain through it. So think of roofs, pavement, sidewalks, anything like that. So to determine this runoff coefficient, we use a weighted average, depending whenever we have different soil types or whenever we have different types of ground cover. And it's a very basic equation. You can see it right there. It's the sum of the area times the runoff coefficient for that type of soil divided by the sum of all the areas. And once we get that number, we can go ahead and determine the peak runoff for the pre-development condition. Again, that's the amount of water leaving over there where we see that area C. And that equation is the runoff coefficient times the design intensity, and this intensity would be given by the municipality per the requirements, times the drainage area that we're working on. So for this case, we can see we have 2 types of soils, soil A and soil B. A is 0.2 acres and has a runoff coefficient of 0.1, and B is 3.3 acres and has a runoff coefficient of 0.2. So the discharge will be in cubic feet per second. The runoff coefficient is unitless. Then we do the drainage areas in acres, and the rain intensity will be given in inches per hour.
One thing I want to point out here is this equation, the Q equals the C times the I times the A.
Right.
If you guys try to work out these units, you're going to think we've got to do a lot of conversions of the units. And what's funny is if you actually did the conversions, it becomes a factor of 1.008. And us being civil engineers, as opposed to structural engineers or chemical engineers, we kind of round everything. So it's kind of an engineering standard that in this one equation, you don't have to worry about converting the units. So we have 2 equations here. Obviously, one, you get an answer, and then the answer from the first equation gets plugged into the second equation. This CW that we calculate in the first equation gets slid down as the Q pre below. Here's the actual, results or calculation written out. So what we call this, and I'm not sure if this is a math term or not, but we call it a weighted average. And so you run through those numbers from the map on the previous page, the 0.2 acres, the 3.3 acres, and you get that C of 0.19. It gets plugged in down here. We've got the 7.08, which is given, and that's the total acreage where we added the soil A and the soil B areas together. And you come up with, 4.7 cubic feet per second. So with that, we could move on to the next one, which is essentially the same calculation, but now this is the post-development conditions where you can see that that blue area has now gotten very large. Now we're not worried about soil conditions because we're manipulating the land, but we have what we're calling impervious, which is the blue color. And then the edges we're calling, where we have grass and landscaping, we're calling that pervious. And those also have runoff coefficients that differ for that. And just to explain that a little bit, the impervious, the blue area, which is our roofs and our pavements and our sidewalks, the runoff coefficient is 0.95. And really what the runoff coefficient is if you had a runoff coefficient of 1, that would mean all the water that fell on that surface would accumulate and run to one point. Even though if we've got pavement and roof, some of that we get some evaporation, we get some absorption. So that's why it's not quite 1, it's pretty darn close though. You go down to the grass and the landscaping, that coefficient is 0.35 because we get a lot more of it infiltrating into the ground and evaporating, plants absorb it. So that gives you an idea what that coefficient means. Now, obviously 0.95 for the impervious areas and 0.3 for the grass areas are both much higher than our old peanut farm. So not only do we have a much bigger area, but now we have surfaces that are not absorbing as much water. So again, the math in this page is the same as it was in the previous one. It's just now we're doing the after conditions. Those exact same formulas, just different numbers in there. And what was it, 4.7 is now about 10 times as much. We're almost at 47 cubic feet per second. Now what we do is we compare this 47 CFS after construction compared to that 4.7 from before. And obviously the conclusion is our post runoff, which is Q post, is much higher than QP, so we need a stormwater device. Architects have to design around a building code, and it's statewide. So there's one code that they need to know. Ours varies. Garner has different rules than Apex, which has different rules than Wake County, which has different rules than the state of North Carolina. So in general, it starts with the state, and then the state gives the local counties an opportunity to come up with their own requirements. And if they are, equal to or more stringent than the state, then the county can do it. And then it goes down to the town below that. We do some work in maybe some more rural counties, and they have no codes, which would then fall back to the state. And again, even throughout the state, they vary depending on what river basin you're in. I think Danny showed a slide with a map of North Carolina that had all the different river basins. And around here, we've got the Neuse River or the Cape Fear River, I think covers most of Wake County. And those are two of the more stringent in the whole state. You go out west and you may not have any requirements. We had a big fish kill in the Neuse River back in, I can't remember if it was the late 90s, that really triggered a lot of the stormwater codes we're dealing with today, and also stream buffers and maintaining, wooded buffers along streams. Things changed dramatically in the early 2000s.
The Neuse River Basin is one of the most polluted. It's also one of the smallest basins. It also, right at New Bern, discharges into the largest estuary on the East Coast. So that is one of the reasons we picked this site. That is a very small river basin, and it's very urban. And as a result of it, and you see it goes into the Pamlico Albemarle estuary. And I believe actually it's one of the largest estuaries in the country. So yeah, it's a big deal, and that's why the regs are so strict.
So the next set of calculations I think what we talked about at the beginning was in the corner of this school site, in a couple of the corners, we've designed stormwater wetlands. And so we were concentrating on that one wetland in the bottom right-hand corner. so that wetland's going to be designed to hold water back and release it slowly so we don't cause flooding problems. But it's also going to hold water back and filter it and allow plants to, remove the nutrients. And in our business, nutrients in stormwater is a bad thing. Okay, having nitrogen and phosphorus in stormwater is a bad thing. We try to get that out. If it goes right through our site and goes into the Neuse River, those nutrients get in there, and all of a sudden algae likes those and starts to eat those, and the algae starts to bloom and get really heavy, and then it blocks sun from getting into the water and allowing the normal native plants to grow, and that's why you get fish kills. So we're trying to get nutrients out. So the wetland is something that's been proven to be able to do that. And this page has 3 calculations on it. The first calculation is calculating what they call a runoff volume, or runoff value. And so you take that, what we're showing here is the percent impervious, obviously the impervious area within the wetland drainage divided by the total area. So it would be the 6 acres of impervious divided by 8.7. Pretty simple. That then gets plugged up into this calculation, and you end up with this RV value. That RV then gets pulled down into the next equation, where we're calculating the volume of our wetland that we need. And that's a pretty simple algebra, obviously, or not even algebra, arithmetic, I suppose. There's some givens here. The first given is the design storm. And for most places in North Carolina, we design for 1 inch of rainfall. That's 90% of our storms are 1 inches or less. And those also where you're getting what they call the first flush. So when that first rainfall hits these impervious surfaces like pavements and roofs, that's what's washing the oils and the acid rain that it accumulated on the roofs. That's what washes it into our wetland. Once we start getting these huge rains that go on for days, by that time, all those pollutants, or most of those pollutants, are already washed off, and we're getting much cleaner water. So that's the 1 inch. And we said Fuquay Marina because that's where we are. The runoff volume we bringing from the calculation above, and then the drainage area, which is just the area draining to our wetland, which was the 8.7 acres. And we get a required volume. Now the one thing here, note we said we've got a unit conversion here. This is one where we do have to convert units. We have to convert acres to square feet so that our answer comes in square feet. Lastly, we're calculating the area. So the wetland design is a volume of water that we need to capture, and then we also have to spread it out over an area. And wetlands, unlike ponds, are shallow. So we have our volume, and we're pretty much dividing that by our average depth. And so the average depth is given as 15 inches. So we got a simple conversion there from inches to feet, and we get an area required. So the next slide is kind of us working that number out. Sorry, I had to cram them in here. The first part is where we did the percent impervious, 69%. We plugged that into the RV calculation. And on that, you actually use the 69. You don't use 0.69. So we get our RV value. We plug that into the next equation. And the trickiest part about that next equation is probably the unit conversion. So that's why we're showing in this first line is the whole unit conversion, where you write out all the units and you cross out how acres cross out acres, inches cross out inches, and then we end up with cubic feet. And then finally, we take that cubic footage. Sorry that, I don't know if that keeps popping up on your screen. And we convert that to the area. And now we have a required area for our wetland of 17,000 square feet. And I showed this, the math came out to 16,927 square feet. But like I said before, we're toting water, we're not making watches. So as engineers, we usually round up. We try to be a little more, give ourselves a little wiggle room. We don't design things to the decimal place or to the actual square foot. If anything, we want to make our wetland a little bigger than it needs to be. The next one is, I think, bringing in a little more, maybe some geometry into it. This is kind of a cross section of a wetland. We've got a channel going down the middle of the wetland. The dark blue in that cross section is where we will always have water in the wetland. We have a channel down the middle that's a little bit deeper that allows wildlife to travel through there. When it does rain, that's where most of the flow is going to be. If we do get an extended drought, that could stay wet and sustain our bugs and our reptiles and our amphibians that are living in this wetland until it rains again. But basically the dark blue is what we call our permanent pool. It's the permanent water in there. And then on top of that is where we have to store that volume that we just calculated. I'm gonna pop back and remember what that volume was. It was that 21,000 cubic feet. So the 21,000 cubic feet is what's in that light blue area. And that's only 15 inches deep. And so we're doing a calculation here. We call it average end area, where we're kind of splitting that into two sandwich slices of the light blue area. And you can kind of see how the top slice, the sides of it are almost vertical. So it's almost like a cube. Whereas the lower slice, we have this very gentle shelf. So it's becoming more of a trapezoid, or a more exaggerated trapezoid. So this equation is just doing that math. So it's just working volume of wetland. And we do this, and the way we do it in design is we had that 17,000 that we're working towards, and we came up with an area, and that's where kind of the landscape architecture comes in. In kind of the experience and the art part of it, where you're just kind of working with shapes, what fits in the land well. We do want to be a little bit more than the minimum required. We want to have a safety factor in there, because we have to remember that this is ultimately built by guys driving huge equipment, pushing dirt around. So they're not going to get it exactly right. We want to give them a little bit of a wiggle room. But the solution here, we come up with the volume that our design has provided, and we see that it's greater than what's required, so we're okay to move ahead. One thing I wanted to reinforce was these two calculations. The shallow land, just as a reminder, that's the area around the outside. It was the green area. That's going to be mostly, under normal circumstances, dry. It might be a little damp, but it's generally above the water level. And then the shallow water, where he's putting the herbaceous plants, that's the blue area. So those need to be plants that are continuously wet. Things that you see growing up through the water. Take a mental picture of this, of the different colors, because this next slide, you can kind of see it soon after it's been graded in. Now this is from being up at the top of the hill at the school site. That box in the upper corner is the outlet structure. So the pipe leaving that heads towards the intersection and joins the town's water storm drain system. But you can kind of see the wet area there is the shallow water, and the brown is the shallow land. There's some deep pools in there. I think if we look really close, we could probably see those. And then the grassed areas on the top is the embankment. And I think you can kind of see the shape of that. You can kind of see a steep slope here and then a flat area at the top. And obviously the grass on the bottom is that steep slope going up towards the building. So this page, we just kind of summarized the calculations that we went through, determining the percent of impervious, the runoff coefficients, determining the volumes required and making sure we need a wetland. And then so we're just kind of going back to what all we already did. And then we went to, doing the plantings and how many herbaceous and shrubs we need. And then here it is after it's been newly planted. You can kind of see the shrubs growing on the land and stuff popping up through the water in the shallow water zones. And finally, here's our actual wetlands. Some of these are familiar pictures. It progressing during construction, right before we planted it, and after it's been planted. You can see the clarity of the water, really brown and orange during construction with all that clay coming off the site and those clay particles just suspending in the water. And as it's getting cleaner is mostly due to the contractor is stabilizing the site with grass and landscaping and paving. We don't have as much exposed clay. And I think you'll see like Jordan Lake and Falls Lake look brown most of the time because their drainage areas are so huge. Somewhere in there's a lot of construction going on. And it's getting to it. Here's a nice aerial of our actual site with the wetland kind of in the right-hand side. You can see that steep slope coming down from the school building. Kind of see our shallow water, shallow land areas. That wasn't an aerial we took specifically for the wetland. I think the contractor was trying to get the building mostly, but he's had a little bit of the wetland in there. And then the picture on the right is not our wetland. Our wetland is not mature enough to look like that yet. But this is at Beaver Dam Elementary School that was built a couple of years ago. And that's what we're going
so that shows you that is literally 2 years of plant growth. And look at how significant. You can see the lily pads. Behind the lily pads, that's all pickerel weed. So literally in 2 years, that is the transformation of the constructed wetland into the plant. And you can see the riser structure in the background. Now it's not prevalent at all. So yeah, these become very, what I love is when I took these pictures of Beaver Dam Elementary School a few weeks ago, the amount of wildlife that I flushed out just walking down to the edge. So it's amazing how fast they transform, and the water's crystal clear.